Hey everyone, welcome back. So glad you are here for this one. If you are new, quick context. This is episode 4 of the sliding window series. Episode 1 was the intro, episode 2 was fixed size windows, and episode 3 was variable size windows. But jumping in right here, completely fine. I will give you everything you need. Now today's problem. You are in a FAANG interview. The question appears on the screen. Given two strings S and T, find the minimum window substring of S that contains all characters of T. You read it. You think, okay, I know strings. I will just scan every possible substring and check if it contains all of T. Then the interviewer says S can be up to 100,000 characters. And that instinctive heart, that brute force, it just died. Because checking every substring of 100,000 character string is not just slow, it's catastrophically slow. We are talking billions of operations. But here is what this episode is about. By the end, you will look at this problem and see exactly why a two-pointer approach collapses it to a single pass. Often, one direction, no going back. And more importantly, you will understand every line of the solution, not just copy it, understand it. Alright, let's build it from scratch. Quick orientation before we dive in. Episode 1, what is a sliding window? Episode 2, fixed size, size K, never changes, like a camera with locked zoom. Episode 3, variable size, no fixed size. Expand when things are good, shrink when something breaks. Today, episode 4, we are on the same variable window idea, but something important is different. In episode 3, the condition was simple. Is this character already in the window? Yes or no? A set handled it perfectly. Today, the condition is harder. Does the window contain all characters of T with the right frequency? Not just is A in here, but do I have enough A's, enough B's, enough of everything? That shift from presence to frequency is the entire upgrade, and it forces us to change one thing about how we track the window. Everything else stays the same. That's the promise of learning patterns. The skeleton does not change. You just learn what to swap. Okay, let's get the problem statement airtight. Given strings S and T, return the minimum window substring of S such that every character in T, including duplicates, is included. Return empty string if no such window exists. Two things to lock in before we move on. First, including duplicates. This is not just does A appear somewhere in the window. If T equals AAB, the window needs two A's and one B. Frequency matters, not just presence. Second, minimum. We are not just finding a valid window. We want the smallest one. Let me show you the three examples on screen and I want you to read them, not just hear them. S equals ADOBECODING. T equals ABC. Answer is ADOBEC. Length 6. S equals A. T equals A. Answer is A. Exact match. S equals A. T equals AA. Answer is empty string. T needs two A's. S only has one. Impossible. That third one, that's the one that catches people. A set would say A is in the window. We are good. But we need two A's. A set can't tell you that. Pause here for a second. Think about this. How would you check if a window has the right frequency of every character in T? Not just presence, frequency. Okay, Let's look at why the first instinct breaks and what we actually need. So here is the natural thought. I used a set in episode 3. It worked great. Let me just use it again. In episode 3, the set tracked one thing. Is the character currently in my window? And the condition was no character appears twice. Set handles that perfectly. O of 1 lookup. But let's stress test it. T equals ABC. I need 1A, 1B, 1C. My set says, does the window have A? Yes. B? Yes. C? Yes. We are good. But what if T equals AABC? I need 2 A's. My set still says, does the window have A? Yes. But it has no idea if there is 1A or 5 A's in there. A set tracks membership, not quantity. So we need to stop asking, is this character here? And start asking, do I have enough of this character? That means switching from a set to frequency maps, dictionaries. Here we will be using two frequency maps. One need built once from T tells us how many of each character does T require, and window updated as we expand and shrink tells us how many of each character does the current window have. But here is the clever part, and this is the real insight of this problem. Checking window equals need every step would mean comparing two entire dictionaries. That's O of k every time. We would do it n times. Not great. So instead, we track a single integer called formed. Formed is the number of characters in T that currently have their required count satisfies in the window, and required the total number of unique characters in T. When formed equals required, every character has its required count. Window is valid. One integer. That's it. That's the trick that keeps this O of n. Okay, now I want to give you the full mental model before we touch any code or any example. Because once you have this model, everything else, the walkthrough, the code, the edge cases, all of it just falls into place. 4 steps. This is the algorithm. Step 1. Expand. Move R forward. Add S of R to the window. Update window of SR. Now, did that addition just satisfy a required count? If window of C equals need of C, yes. Increment formed. Step 2. Check. Is formed equals required? If yes, the window is valid. Every character of T has its required frequency. We have a candidate answer. Step 3. Track. While the window is valid, compare its size to the best we have seen. Update if it's smaller. Record L and R. Step 4. Shrink. Still inside the valid window. Move L forward. Remove S of L from the window. Did that removal break a required count? If window C less than need of C, yes. Decrement formed. Window is now invalid. Go back to expanding. Notice the shape. We expand until valid. We track and shrink while valid. We keep going until R hits the end. L only ever moves forward. R only ever moves forward. That's what makes this O of n. We will come back to why, but hold that thought. Let's run through the example by hand. S equals ADOBECODING. T equals ABC. Need equals A with 1 count, B with 1 count, and C with 1 count. And required equals 3. We need formed to reach 3. Follow along with the table on screen. Step 1. R is 0, character is A. Window of A equals 1. Does window of A equals need of A? Yes. Formed equal to 1. 1 out of 3. Keep expanding. Step 2. R equals 1. Character is D. T is not in need. We add it to window anyway, but formed does not change. D is irrelevant to our goal. Still 1 out of 3. Step 3. R is 2. Character is O. Same story. O is not in need. No effect on formed. Still 1 out of 3. Step 4. R is 3. Character is B. Window of B equals 1. Window of B is equals need of B. Formed equals 2. 2 down, 1 to go. Still not valid. Step 5. R is 4. Character is E. Not in need. No effect on formed. Still 2 out of 3. Step 6. R is 5. Character is C. Window of C equals 1. Window of C is equal to need of C. So formed equals 3. Formed equals required. Valid window. Current window ADOBEC. Length 6. That's our best so far. Now we don't stop. We try to squeeze it. Step 7. Shrink. Remove S of L equals A. L moves to 1. Window of A drops to 0. 0 is less than need of A, which is 1. Formed drops to 2. Window is now invalid. Stop shrinking. Step 8. R is 6. Character is O. Not in need. No effect. Still 2 out of 3. Keep expanding. And it continues. R keeps going forward, trying to collect A again. L never goes back. Both pointers travel in one direction. That's the whole story. Key observation right here at the bottom of the slide. L only moves forward. R only moves forward. Combined, they make at most 2n moves. That's O of n. No rescanning. No repeated work. Okay, we just traced through the whole thing by hand. We know exactly what needs to happen at each step. Expand, check, formed, track the minimum and shrink. So instead of me just showing you the finished code, let's write it together, live, on the actual LeetCode problem. I want you to watch why each line gets written, not just what it says. Switching over now. LeetCode 76. Minimum window substring. This is the exact problem we just traced. S, T, smallest window that contains everything in T. Constraints, I will point at one thing only. S and T can be up to 100,000 characters. That's the line that kills brute force. That's why we are here. Alright, let's code. First line, edge case. If S or T is empty, there is nothing to find. Return empty string immediately. One line, done. Now our two maps. Need built from counter T. This is the rule book. How many of each character does T require? Built once, never touched again. Window, a default dict. This is the live tracker. What's currently sitting between L and R. Now formed and required. Required. How many unique characters does T have? That's just length of need. That's our finish line. Formed starts at 0. Climbs every time a character in the window hits its required count. When formed touches required, the window is valid. Left pointer at 0. Best length starts at infinity. We have not found anything yet, so we set the bar impossibly high. And best L and best R, these are not just for the length. We need the actual slice at the end. So we save the boundaries every time we find a better window. Now the main loop. R moves forward every single iteration. No conditions, no skipping, always forward. That's the expand step. We add every character to the window, even characters not in need. D, O, E, they all go in. But this next line is the important one. We only increment formed when two things are true at the same time. The character is in need and its count on the window just hit the required count exactly. Not exceeded. Hit exactly. Why exactly? Because if need of A is 2 and window of A goes from 2 to 3, we don't want formed going up again. That character was already satisfied. The condition catches only the moment it tips over the line, not every time after. Now the inner while loop. This is where the magic happens. This loop only runs when formed is equals required, meaning every character in T has its count satisfied. We are in a valid window. And while we are valid, we do two things: track the minimum, then shrink. Track first. If the current window is smaller than anything we have seen, save it. Save the length, save the left and right boundaries. Now shrink. Remove the character at L from the window. Then, did that removal just drop a required character below its needed count? If yes, formed goes down. The while loop condition fails. We stop shrinking and go back to expanding. And finally, the return. If best length never moved from infinity, we never found a valid window. Return empty string. Otherwise, slice using best L and best R. That's our answer. Let's run it. All green. Clean pass. Let's submit it. The code submitted successfully. Now let's go back. Same code on the slide. And I will walk you through 5 specific things that are easy to miss when you are writing it for the first time. Okay, same code now on screen cleanly. No distractions. We just wrote this live, so nothing here should surprise you. But I want to go through 5 specific things because understanding why each piece exists is what separates someone who can reproduce this from someone who truly owns it. Let's go line by line. Number 1. The edge case at the top. If S or T is empty, there is nothing to do. Return early, one line. Don't let the rest of the function run on empty inputs. Second, need versus window. Need is built once from counter T. It never changes. It's the rule book. Window tracks what's currently between L and R. It grows when R adds a character and shrinks when L removes one. Third, if ch in need check. And why we only count characters that matter. We add every character R encounters to window, D, O, E, all of them. But we only increment formed when a character in need hits its required count. Characters not in need are invisible to formed. They are passengers in the window, not contributors. Fourth, the while loop, and this is important. You might wonder why while and not if. Here is the thing. Once the window becomes valid, we want to shrink it as much as possible before it becomes invalid again. We might shrink 10 characters before the window breaks. If would shrink once and walk away. While keeps going until the window actually breaks. Fifth, best L and best R, not just best length. We track both the length and the boundaries because at the end we need to return the actual substring, not just its size. S of best L to best R plus 1 uses those saved pointers to slice the answer. One thing worth noticing, best L and best R are initialized to 0, 0. That looks like it could cause a bug, but it's harmless because if no valid window is ever found, best length stays infinity and the return statement gives back empty string before those values are ever used. complexity. And let's make this human, not just symbols. Brute force O(n) squared. Every pair of indices is a potential substring. That's already O(n) squared just to generate them, before you even check if they are valid. Interview strings go up to 100,000. That's not just low, that's a hard timeout. Sliding window is O of n. Here is why in plain English. R visits every character exactly once, left to right, no going back, n moves. L also only ever moves forward. It can never overtake R. So it makes at most n moves too. Together, at most 2n moves. That's linear, O of n. Think of it like two people walking the same road in the same direction. One leads, one follows. Neither one turns around. Combined, they walk 2n steps. That's it. No rescanning, no repeated work. Space is O of k, where k equals unique characters in T. In practice, for lowercase English letters, that's at most 26 entries in each dictionary, effectively constant. Brute force, quadratic, or worse. Sliding window, linear. Same correct answer. One of them just does not waste the machine's time. Edge cases. I know it's tempting to skip this section. Don't. In an interview, the happy path gets you to OK. The edge cases gets you to higher. Empty S or T. Handle it in the very first line. Return empty string immediately. Don't let your counter or your loop touch an empty input. S equals AB, T equals ABC. C does not exist in S. R travels all the way to the end. Formed never reaches required. Best length stays infinity. Return empty string. Duplicate characters in T. S equals AB, T equals AAB. This is the one that would silently break a set-based solution. T needs two A's. The window must collect window of A equals 2 before formed increments for A. 1A is not enough. Counts matter. S exactly equals T. S equals ABC, T equals ABC. The whole string is the answer. Formed hits required at R equals 2. Best window is the full string. Then L tries to shrink. Every character is at exactly its required count. So one removal from L is enough to break formed. The window cannot shrink at all. Returns ABC. T longer than S. S equals AB. T equals ABCD. Impossible by definition. Formed will never reach required. Return empty string. A character in T that does not exist in S at all. S equals ABCD, T equals ABZ. Z never appears. Formed can never reach required. Return empty string. Pro tip: after you write your solution in an interview, spend 60 seconds walking these cases out loud. You don't even need to run them. Just say if T has duplicates, the formed counter handles that because we only increment when window of C hits need of C exactly. One sentence. That's the signal of someone who actually understands the code. Okay, this is the slide you want to screenshot because this pattern, this exact skeleton shows up across a whole family of problems. And once it lives in your memory, you stop solving them one by one. You just recognize the shape. 4 bits, always in the order. Expand, R moves forward, R to window, check if formed goes up. Valid, formed equals required, means every required character is satisfied. Track, while valid, record the smallest window seen so far. Shrink, remove from the left, check if formed goes down. Move L. What changes between different problems? 2 things only. What need is built from. Sometimes it's a target string, sometimes a number. The condition that makes formed go up or down. Today it's frequency match. Next problem it might be something else. The shape stays the same. You just swap what valid means. Alright, before we wrap, let's zoom out for 1 second. Look at these 6 problems. All 6. Different numbers, different names. But every single one of them runs on the same template we just built today. Episode 3, longest substring without repeating. LeetCode number 3, variable window plus a set. Done. Episode 4, minimum window substring. LeetCode number 76. That's today. Frequency maps, formed counter. Done. Now the ones marked next. Number 567. Permutation in string, fixed window, character counts. And number 438. Find all anagrams in a string, fixed window, frequency match. If you understood today's problem, those two maybe 20 minutes each. And coming after that, number 424. Longest repeating character replacement. Variable window with a max frequency trick. That one has a moment that will make you pause and go, wait, that's actually clever. Number 1004. Max consecutive ones 3. Variable window, K flips. Clean problem, clean solution. Master the template once and you can solve 10 plus problems. You are not memorizing 10 different solutions. You are learning one mental model and applying it with different constraints each time. That's the whole point of this series. Quick look at where we are in the series. Episode 1, Intro to Sliding Window. What even is a window? Done. Episode 2, Fixed Size Window. Max sum array of size k. Done. Episode 3, Variable Size Window. Longest substring without repeats. Done. Episode 4, Minimum Window Substring. Flagship problem. Combines everything. That's today. You are here. And coming up, episode 5 and 6. This is where you apply what you learned. We take the fixed window concept and bring in frequency matching. 2 problems, permutation in string number 567 and find all anagrams number 438. Same fixed window logic, just checking character counts instead of sums. Episode 7 and 8. Variable window with a twist. Longest repeating character replacement and max consecutive ones 3. These ones have a clever trick we have not seen yet in this series. The series is structured on purpose. Every episode builds on the last. So if you have been watching in order, episode 5 is going to feel easier than today, which is great feeling after this one. Subscribe so you don't miss it. And that's episode 4. 4 steps. That's all minimum window substring is. Expand, check, track, shrink. If any part of this clicked for you, hit that like button. It genuinely helps this channel reach more people who are grinding DSA. If something didn't click, drop a comment. Tell me exactly which part confused you and I will address it in the next video or reply directly. And subscribe because episode 5 is permutation in string, fixed window plus character count match. It's a step down in difficulty from today, which makes it the perfect follow-up after this one. Thanks for watching. Learn smart, code calmly, and I will see you in episode 5.